Okay, welcome back to the second video. What we're going to do is we're going to work through one of the examples from the textbook. I know it's a little bit confusing to look over, but I'm going to try to simplify it for you, just in my own way. So if you were checking on page 360, there's worked examples 1, and it doesn't really go over how to work over the example. So that's what we're going to do. So it basically says, you know, the question is that we need to write the enthalpy change of formation of potassium bromide. Write an equation for the formation of potassium bromide. So we know we want to form potassium bromide, KBr, and the delta H of formation, right? Delta H of formation. What that means is that we want to react elements together in their standard states to form potassium bromide. So the standard state of potassium metal is a solid, Ks, and the standard state of bromine is bromine gas plus Br2. Br2 forms KBr. And we can balance this out. We can either write, double this up and then double this, or we can just write that it's half a bromine, because then in that case, it's kind of like we're reacting K plus Br together to form KBr. So you can see it's kind of like the 1 to 1 to 1 mole thing, because all of the values that we get are kind of, 1 mole. The energy required to ionize this, or the electron affinity of this, it's only for 1 mole of this, not for 2 moles of this. So this just simplifies it a little bit if we just deal with 1, 1, and 1's exact values. Okay, so that's the equation that we're going to be looking for. So you write that equation right at the bottom. K, potassium solid, plus bromine gas, so I should have that gas right there, reacts to form KBr. So now we kind of think endothermic processes on the left and exothermic processes on the right. So in order, our first one, we need both of these, right? We need them both at the top to be potassium metal plus bromine plus 1 electron. And we're going to see how we can assume that in a second. So anything that gets us to these values. So basically, let me just do 1/2 Br2. So basically, we've got potassium as solid. Our first one, we should get potassium to a gas state, because this is always in gas state and this is always in gas state. Sorry, I've got the hiccups right now. So in order to change the potassium to the gas state, we need to input energy, right? This is an endothermic process, delta H of atomization. And we're going to change to potassium in the gas state. And this value is going to take energy, so it's going to be 89 kilojoules per mole. Okay, so that's our first step. So now we've got potassium in the gas state, and we're still reacting it with 1/2 Br2. But we want to get rid of that Br2, right? We don't want to be reacting Br and Br. We want to be reacting K and Br. So we need to use the bond enthalpy to break it apart. Or for gases, diatomic gases, we also call this atomization. So let's do the second step. We'll do delta H of atomization of Br2. And that value is going to be 97 kilojoules per mole. And what we're going to end up with is K as a gas plus Br as a gas. And now we're almost there. Sorry, K plus Br. Oh, never mind. Sorry, that's my equations right here. I messed that one up. Okay, and then to get to this last one, we need to somehow knock an electron off. And knocking an electron off is an is an endothermic process. So the last one, it's delta H of ionization energy of K in the gas phase. And that value is going to be 419 kilojoules per mole. So then we finally ended up here. So we've taken solid potassium, we've turned solid potassium into gas potassium, potassium in the gas phase. We've broken the bond between bromine. So we've broken the bromine-bromine bond, and that was our delta H of atomization of Br2. And then finally, we've ionized K+ to form potassium ions, and we got to leave this electron right here. So then we start to work through our exothermic processes. So we go down, and in exothermic processes, so electron affinity is typically exothermic. It's typically exothermic. So bromine reacts with this electron to form bromine ions. And this is delta H of electron affinity. And that value is going to be a negative value. It'll be negative 325 kilojoules per mole. And the whole question, what it wants, so we got Br negative plus K positive, and they're both in the gas phase. And what this question wants is we've got potassium bromide in the solid phase, and it wants to know this value. It wants to know this delta H value. And remember, we called that the delta H of the lattice enthalpy. Because remember, the lattice enthalpy was the energy required to turn a solid ionic compound into its constituent ions in the gas phase. And from our textbook, our delta H of formation is equal to negative 392. And this is all in kilojoules per mole. So how do I do this? This is a good question. So how would I do this? Is all you have to do is you add all of the endothermic, add all of the up arrows on the left, and then add all of the down arrows on the left, and that equals your delta H of formation. So let's look at what this is. Let's write this out a little bit. Delta H of formation is equal to you add your delta H of atomization, delta H atomization of potassium, K. You add the delta H of atomization of bromine. You add the delta H of ionization energy. You add, because this is a negative value, you add delta H of electron affinity. And finally, you can flip this arrow. You can flip this arrow down. So it's negative minus delta H of lattice enthalpy. So then you just start plugging in your numbers. Negative 392 is equal to, this is 89 plus 97 plus 419 plus negative 325. So that's 1, 2, 3, 4. And then minus the delta H of the lattice enthalpy. And then we just need to solve this. So let me get my calculator open right here, and we can start to work through this. So we got 89 plus 97 plus 419 minus 325. So here we've got 280 minus delta H of lattice enthalpy, and here we've got negative 392. Then we could just start to solve them all. We can start to say, okay, well, rearrange this, move it to the left-hand side. So we've got, how do I do a negative on here? I'll just add them together because it's a minus and a minus. So 392 plus 280, 672. So this is negative 672 is equal to negative the delta H of the lattice enthalpy. So we cancel off the negatives and we get 672 equals delta H of the lattice enthalpy. And that's our final answer. Delta H of our lattice enthalpy needs to be an endothermic value, right? We can't just take this solid and imagine that it's going to release energy when we break it up, when we turn it into a gas phase. Of course it needs to absorb energy, kilojoules per mole. So your book was a bit wrong on this because your book says it's negative 672, but it's definitely not an exothermic process. You are turning a solid into a gas and breaking an ionic bond, which is endothermic, 672 kilojoules per mole. So okay, join for the next video. I will go over the next example, and then we can work on some more problems together. Thank you.